my name is Jeff, and today we're going to be looking at a Laplace transform problem. In particular, this is going to be a proof problem. I know many students cringe when they hear proof, but I think you'll find it's not that bad. This was a problem on my test, last test in differential equations last semester, and I was really stumped by it, as I'm sure a lot of other people were. So this is the theorem that says that the Laplace of f of t, where f of t is a periodic function. And what does that mean? Well, first we'll look at it graphically. Say you have a periodic function, which means it's regularly repeating. And most of you are familiar with the sine and cosine, I'm sure, functions. So these are examples of periodic functions. And basically, if we just mark a point on the x-axis, for instance, one period regularly repeating, we'll find the same function value. Likewise, we could do this for the crest or the peak of the wave, or we could do it for the trough or any other point. Actually, we could do it here or here, and we will find that the same point has the same function value at that point. So that's what it means when, well, graphically that's what a periodic function is. Mathematically, we say that for f belonging to the domain from 0 to infinity is belonging to the reals for some with period capital T greater than 0. So then f of t is equal to f of t plus capital T for all t greater than or equal to 0. So this states exactly what we saw before, and that is that if you take another point along the wave or the periodic function, you will find if you move forward, if you shift forward by one period, you will get the same function value. This is kind of like f of x, but this is f of t, so it's your height corresponding along the y-axis. This is f of t in this case. So there's the idea. So, and this for a periodic function is going to be how we denote the Laplace, capital F of s. So we want to prove that this is true. Well, how are we going to go about doing that? Well, we're going to break it down. First, we're going to just look at the Laplace of the definition of the Laplace, which is equal to the integral from 0 to infinity of e to the negative s t f of t dt. Now, I think you can convince yourself that this is, if we split this integral up into, say, two parts, but still had it from 0 to infinity, it would still be equivalent. So that's what we're going to do. We're going to say the Laplace of f of t is equal to the integral from 0 to t of e to the negative s, lowercase t, f of t. This is the period, and this is just your dummy variable t, plus the integral from capital T for period to infinity of e to the negative s t, f of t dt. So this is nothing more than a modified version of the definition of the Laplace. So if you look at it, here we have the numerator of our proof, of what we're trying to prove. So all we need to do is somehow make this, put this into the denominator. So we're just going to carry everything along for the ride, and I would highly recommend this instead of sort of just putting an equal sign. just bring these along for the ride. Okay, so what we're going to have is plus, and what we're going to do here, we're going to make something similar to a U substitution that you learned about in Calculus 1. Except here we're going to do a tau plus capital T equal lowercase t, our dummy variable. So if you remember, t plus capital T, f of t plus capital T equals f of t, so that's why this is a good substitution to use, and hopefully that'll become clear. So then dt equals d tau. And lastly, we have to remember to change the limits of integration. So how are we going to do that? Well, we're going to plug in these previous limits into our dummy variable t and evaluate it at that value. So we're going to plug capital T in for t first to get our lower limit, and we're going to get tau equals capital T, replacing that, minus, bringing this t to the other side, minus capital T is going to be equal to 0. So that's our lower limit. And for our upper limit, we have tau is equal to, plugging infinity in for t, we get infinity minus capital T is equal to infinity. Infinity plus or minus any constant number is still going to be infinity. It doesn't change its nature. So 0 to infinity are our new limits. So we're going to put all that together and say from 0 to infinity, this integral of e to the negative s, and then we're going to use our substitution, tau plus capital T, f of tau d tau. And we're not using f of tau plus capital T because we don't need to, because for a periodic function they are equivalent, if you recall what we talked about at the beginning of the video. So, alright, now we have this, and how does this help us? Well, the next step is going to be to pull out the constant term, which in this case is going to be e to the negative s capital T. If you remember, when you add exponents, you're really multiplying the base to the exponent. So this would be e to the negative s t times e to the negative s capital T. So we're going to pull this out of the integrand. So what we're going to get, we're going to just rewrite it again. The Laplace of f of t. I know it gets old, but you get to where you can kind of do this pretty fast with some practice. Plus, okay, so we're going to pull it out, plus e to the negative s capital T times the integral from 0 to infinity of e to the negative s tau, f of tau d tau. Alright, so if we look at this, we can see that we have actually the definition of the Laplace transform. Except instead of t we have tau, but that doesn't matter because it's just a dummy variable. So what we can do is we can rewrite this as the Laplace of f of t. And we can write t because tau is just a dummy variable and it doesn't come into play in the final result. Alright, so now to sum this kind of up, we can basically treat this as an algebraic equation and just move this to the other side. And at the same time, we're going to factor out the Laplace of f of t to save ourselves one step. So we have the Laplace of f of t factored out. We have 1 because it's here already, and then minus because we have a plus here, we're subtracting it. So we have minus e to the negative s capital T equals, and we bring this down, the integral from 0 to capital T, period of e to the negative s t f of t dt. And as the last step in proving this, we say that the Laplace of f of t is equal to, what we're going to do is we're just going to divide this 1 minus e to the negative s capital T over. So we get the integral from 0 to t e to the negative st f of t dt over 1 minus e to the negative s capital T. And if you refer to the original equation, we have demonstrated it. So if you do happen to get this question on a test, don't simply copy down the formula, work it out, show your work, show the steps, take a little time, and you'll get full points. Thank you.